of our numerical method 2 class. So last time when we parted, I think we addressed the proof. We discussed about the proof of the degree of precision of Newton code quadrature formula. We wrote the polynomial, we wrote the function f as the sum of its polynomial interpolation plus the error term. And that's what we integrated. But in fact, for Newton codes, as I mentioned, you don't integrate the function itself, but you integrate this interpolating polynomial, right? Because we know that the function can be represented by its interpolating polynomial. So if you add to the interpolating polynomial the error term, so it gives you the exact representation of the of the function, right? But since the error term is not controlled, I know you can control, but you don't know it exactly, but you can control it. Controlling means that you can find an upper bound to say that, okay, this error will not exceed a certain value. So that's the control over the error. But you don't know it. From numerical method 1, you know that the error term is not known, it's never known. You can control it. So if you succeed to integrate the error term, then you get the expression of your error term, which in fact, because if you have the expression of your error term, you know the degree of precision of the quadrature formula, right? Because we know that if the error, the degree of precision of the method is n, then your error term will be a factor of the n plus first derivative of the function at a certain point. And that is exactly what the theorem gives you, the theorem that we stated last time. So I'm going to share that slide, which is this one. So this is for the trapezoidal rule. We saw that the integral gives us the root plus the error term. You can see that now here we can see the error term explicitly, even though C is not known, right? But you have the structure of your error term. You know how it is expressed. But this C is just a point in between A and B, but you don't know that point exactly. You don't know it. You only know that it's in between A and B. So that's exactly what I was talking about. So the knowledge of this will come from the knowledge of the error term when you express f as the sum of its interpolating polynomial plus the error term. So this weighted mean value theorem for integral is what we use to integrate the error term. So this is the error term. And this first expression is the polynomial of degree n. This is the interpolating polynomial, or the Lagrange interpolating polynomial, if you want. And this is the error term. So if you apply this theorem to this product, to the product, you can see that here you have two functions here. You have this first one, which is a function of x. You can see that psi here depends on x. This psi depends on x. You see it's a function of x. So this is a function of x. And the second one, this is another function of x. So actually, we can write that error term as the product of two functions f and g. Obviously, when I say f is not the original f, right? Just to put it in the form where you'll be applying the theorem. I hope you understand that. When I say, you can write that as the product of f of x to g of x. When I say f of x, I mean, or maybe it's better to write capital F and capital G, right? So that you will not think that when I say f of x, it's a left hand f of x. It's not the same. And I think you should be mature enough to understand when I say you can write it as. It's just a structure. Good. All right. So what I'm saying is that here you have this is a function of f. Obviously, what I was saying is that it is not this f. If I say f is different, it's just to write it in this form. Because we need such a factor to apply the theorem, right? We need the factor of 2. So I will call this capital F to distinguish with this left-hand function f. And this is your capital G of x. So you can see that this is a function of x, this is a function of x. So in order to perform this integral, because you will integrate this f of x, because remember we need the integral of f of x from a to b dx. So we also integrate the polynomial and this factor. And when we integrate this factor, we need to apply this theorem. And for that, we take this out of the integral sign. Sorry, I'm in a class. I already sent you an email to acknowledge reception of the file that you sent. Okay. Okay, so sorry for the interruption. Okay, so what I was saying is this. Because we are going to integrate, we need to identify f and g, right? To apply this weighted mean value theorem, because we need that. We need it. And you can see that this f that we take out of the integral is applied to a certain point c. But the f that we extract out of the integral is just a continuous function of the interval ab. Just continuous. We don't need extra information. And that's the case here. If you look at the assumption, when you perform Taylor expansion. Yeah, because Taylor is as a single point. This is the difference. And please take this. I'm using this opportunity to tell you that the difference between polynomial interpolation and Taylor is that Taylor, for the Taylor theorem, you have a single point. You expand about a single point x0. But with polynomial interpolation, you have many other points, right? You expand, if I can say, the expansion is as if instead of focusing at the single point x0, you distribute, right? You distribute throughout x0, x1, x2, x3. That's why here you have this factor, this product, x minus x0, x minus x, you see. So this is similar to Taylor expansion if you assume that all the points coincide, that is, all the node points coincide with x0. You get exactly Taylor expansion if you apply it here. So this is like a generalization of the Taylor expansion, where now your single point x0 is distributed at many, let's say n plus 1 distinct point. So that's why you have this. All right. Now, if you integrate, this is the integral here. You integrate this. Now you see that this capital F of x is continuous. If you look at, as I was saying, if you look at the assumption, The n plus 5 derivative is continuous. So this is a continuous function. It's continuous. So it satisfies this condition. F continuous on the plus interval a. So that's the key. Now for the second function, this one, the g of x has to be integrable on the closed interval, and the sign should not change. The sign of g of x should not change over the interval a b, meaning that throughout it is either positive or negative. It will not change from negative to positive. You have a constant sign there. That is, it's either positive or negative, above the x-axis or below the x-axis. Only. No change of sign throughout that interval. And here you have this. If you look at this, you see it's a polynomial, right? X minus xk, where k runs from 0 to n, is a polynomial. And we know that the polynomial is integrable. You can integrate the polynomial, always. Polynomial is an integrable function. Right. Okay. So, and its sign does not change also, right, by assumption here in this case. Right. All right, so that is it. So if you apply that, we have the results, right? The rest is just to get that this one out of the integral at the second point C. We get directly. So you see that this is the function here. So if we take that function under the integral, so we are here, EF is this one. Now if we take this function out of the integral, but this is our f, right? That part. You see that E will be at the second point. We take it out of the integral, so we are here now. Right. And you can see that Wx, which is our capital G, as I called in the previous slide, does not change sign on the interval x0 up to xn. So we apply the weighted mean value theorem and we get the result. So take that out, then we'll be integrating it. So this is our error term. Right. So this is general. Now we can go to count. We can now start counting the number of points. When capital N is 1, you have 2 points, right? X0 and X1. Those are the 2 points. Then we substitute that. We know what our Lagrange interpolating polynomial is, right? We know all of them, so we can integrate, right? We can integrate the L0s. It will give us h by 2. That is our weight. And then the error, this one, for n equal to 1, substitute. Compute the integral properly, and then this is what we get. And it gives you exactly the result of the theorem. Okay, so you can do the same when n is equal to 2, 3. You can go up to 3, but for 4, you need a different approach. So I'm asking you to do this as a homework. All right, now let us apply the theorem, this theorem. This one, the corollary of this theorem, almost similar. Well, this is the theorem and this is the corollary. That is a corollary. A corollary is like a consequence of a result, right? When we say corollary, it means that this is a theorem. As a consequence of this theorem, this is what we have. Right. Okay, so this is the theorem that gives us the rules, the various rules. And to the corollary, we have the extra information about the error term. And from that, we have the degree of precision, right, of the various quadrature formula. Right. So we are going to use this formula, this one, trapezoidal, Simpson's rule, Simpson's 3S rule, Bose rule, to compute the following integral. So this is the integral, the function if you want. So this is the function. Okay, so this is the function. And we have equally spaced quadrature node x0, x1, x2, x3, x4. So these are the points that we have. And we know the values of the function at x0, x1, x2, x3 up to x4, denoted by f sub 0. So f sub 0 is f at x0. So in general, in this class, if we say f sub I, this represents the value of the function at x sub I. So always bear this in mind. Right? F sub an index is the value of the function at x sub that index. Right? Writing this is longer than this, so this is a shorthand for this. Right? So the left-hand expression is a shorthand for the right-hand expression. So at each point, we have the value of the function. So it's obvious for you to see that, all right, we can approximate the integral using each of the quadrature formula. Right? Now, if you want to approximate this integral using a trapezoidal rule, remember that for the trapezoidal rule, we just use a single interval. Right? Okay, so here we take the interval 0, 0.5, which is this one. 0 from here to 0.5. So x0, x1. So that's what we use for the first, for the trapezoidal rule. And we know the formula. We know the formula. The trapezoidal rule is h by 2 into f0 plus f1. So h by 2, so we compute h, then we multiply h by 2 into, okay, and then h here for the first interval, sub-interval, is 0.5, because if you take the difference between x1 and x0, is 0.5. So h by 2 will be 0 to 5. So that's why we have here 0.5 by 2. And then f at 0, f at 1. So f at 0 is 1, f at 1 is 1.55152. So which is what you have here. So if you compute that, it gives us this expression. Right. So that is for the trapezoidal rule. But what I want to draw your attention on the fact that all these values will not be the same. Why? Because you can see that the limit of integration varies. It's not the same limit of integration. So we cannot compare these results. Because we are integrating the same function but at different subintervals. Here we integrate for the trapezoidal rule from 0 to 0.5. The next one, which is the Simpson rule, we can see that we integrate from 0 to 1. So it's not the same interval. The 3/8 Simpson rule, you can see that here we integrate from 0 to 1.5. So each time we increment the interval, and this is the last one, the Bose rule, we integrate from 0 to 2. So you agree with me that all these okay, so you just apply the rule. I encourage you to do that as a homework. Right? The formulas are there. Check, verify, use your calculator, complete, and make sure that you obtain the same result. Okay. Now, if you want to compare, because I told you that we cannot compare this, the integral, the limit of integration are different. Now, if you want to compare the efficiency of trapezoidal rule compared to Simpson or vice versa, we need to keep the same interval. And the best way for us to do that will be to use what we will call later on composite rule. Composite rule. But for now, let us look at the example. So here, we want to use the trapezoidal rule and the Simpson rule to compute the same integral, you see that now we fix the limit of integration from 0 to 2, right? Unlike here where we are changing the limits of integration. Here, the first integral is we use the trapezoidal rule, but the limit is from 0 to 0.5, whereas for the second one it's from 0 to 1. So we cannot compare because, as I mentioned already, the limits of integration are different. But if we want to compare, we have to fix the limit of integration and apply. Now, let's look at this one. Now, the actual integral, I, because this function is, you can find its antiderivative is just a polynomial. We can find the exact value of the integral, which is 8/3, right? 8/3 gives us 2.667. 2.667. That's the exact value of this integral. Now, if you use the exact limit of integration, that is from 0 to 2, we can use our trapezoidal rule. In that case, our x0 will be 0 and our x1 will be 2. So that's exactly what we do here for our trapezoidal rule. H by 2. H is already 2 because from 0 to 2, that length, if you take the difference, the step from 0 to 2, the length of that step is 2. So H is 2 in this case. So if you divide H by 2, it will be 2 by 2, which is 1. So our trapezoidal rule will give us 1 into F0 plus F1. So F0 is 0 squared. X2 is 2. So F of X2 or F sub 2 is 2 squared, which is 4. So you can see that if you use the trapezoidal rule to evaluate this integral, we get exactly 4. Now for the Simpson rule, since our limit of integration is fixed, similarly for the Simpson rule, we fix that interval to 2. That is from 0 to 2. That is fixed. Now what will change will be the number of sub-intervals, because remember that if you look at the formula for the Simpson rule here, you have 2 sub-intervals. You have the first sub-interval from 0 to 0.5, and then from 0.5 to 1. So there are 2 sub-intervals. Right. So that's exactly what we have here. You have 2 sub-intervals. So you take 2 steps from 0 to 2. So meaning that one step, the length of one step will be 1. So H is 1. Let me illustrate it properly here. So this integral interval is this. A is 0, B is 2. For trapezoidal rule, we know that we only have one sub-interval. So this will be our H for the trapezoidal rule. That is 2. Now for Simpson rule, we know that we need 2 sub-intervals. So if I take 2 steps to reach B, of course, step of equal length, so it means that there will be a point here this thing is fighting with me. All right, so it's there. So we have the first step here. Oh, okay, so we have the first step here and then the second step there. Right. So meaning that a single step here for Simpson is this one step by 2, which is 1. I hope you understand now why here we say H is 1. This is the explanation. Okay, so h is 1. So if you apply the Simpson rule, right, the Simpson's rule, which is this one, this is Simpson's rule. We have two sub-intervals. You can see that here we have x0 to x2. So there are two sub-intervals. The first x0, x1, then x1, x2. So there are two. So it's h by 3, and then this sum, weighted sum, f sub x0 plus 4, f sub 1 plus f sub 2. So if you use that, h is 1, so 1 by 3, f sub 0 plus 4, f sub 1 plus f sub 2. Then we know f sub 0 is 0 square. 4 times f sub 1 is 1 square, plus f2. 2 is, f2 is, what am I saying? It's 2 square, which is this one. So this will be 4 plus 4, 8. 4 plus 4, 8 by 3. You can see that with Simpson rule, it gives us the exact, you can see 8 by 3 gives us exactly the integral. You can see it from here. This is not witchcraft. If your eyes are open, you will see that it gives you exactly 8 by 3, which is the exact value. Right? So Simpson rule here gives us the exact value. Why does Simpson rule give us the exact value? We will see that later on, right? For now, we retain that Simpson rule gives us the exact value for x squared, not for an arbitrary function, but for a particular function of this form, x squared. Clear? Great. Okay, we introduce the composite rule. Why is, sorry, I'm in a class. Huh? Okay, thanks. Okay, so the Simpson, I was asking, why do we need composite rule? Why are composite rule important? Now, look at this previous case. If you look at this example that we just dealt with, this one, we just addressed this problem. We saw that in order for us to compare the Simpson rule with the trapezoidal, we need to fix the limit of integration, right? Unlike in this case where you can see that the limits of integration is changing, we need to fix to compare. And for that, you can see that here, the trapezoidal rule underperforms. Here, instead of 2.66, we have 4. So it gives us a very bad approximation. But why is it that so? Why is it that it gives us a bad approximation? Because we only use one step, right? For the Simpson rule, we can only use one step. That's the reason. So meaning that if you have a very long interval, h will also be very large. Now, the purpose of introducing the the composite rule is that I can decide, no, let me just use my Simpson rule. But if I use Simpson rule, I should be able to use a partition of that interval instead of using just one sub-interval. Why can I use many sub-intervals but still apply my trapezoidal rule? So that is the idea here. I can decide to use a particular formula but with many sub-intervals, because we know that a formula, even though the formula is not good, but it can still converge if you use many sub-intervals or if we increase the number of sample points. That's what we know from numerical methods, right? even if you have something that doesn't perform well, if you take the length of the subinterval over which you perform your computation to be very small, right? As the step goes to 0, your rule should be able to converge. That is the idea. So for us to be able to do that in this setting, we need to introduce the concept of composite rule. Because composite rule will allow us to partition our interval instead of fixing from 0 to 2 and use just one subinterval in which h, the step size, will be very large. We can also decide to reduce our step size. And for that purpose, we need to partition our interval. So that is the idea behind composite rule. We can do it not only for trapezoidal, but we can apply it to any other rule. I hope it is clear. So for Simpson, or for any, let's say for the composite rule, this is the idea behind. Okay, for any Newton code, which means trapezoidal, Simpson, Bose, Rolls, okay, all those. So for any Newton code rule, one can obtain more accurate results by proceeding as follows. Exactly as I said, you partition your interval AB into n subintervals, and you compute an approximation on each subinterval. And then you add up all those approximations to obtain the global result. Right. For the interval AB, this is a partition. We can partition our interval AB into subinterval x0, x1, x1, x2, x3, x, and so forth up to xn minus 1, xn. Those will be the partition. And now you can see that over this partition, our definite integral from a to b, f of x ds, can be written as a sum of the integral over each subinterval of the partition. So we have this. So this integral can be broken into smaller subinterval, and then we sum them up. So these two are equal. Now you can see that in the smallest subinterval, we can perform our rule. And this rule that we perform in each subinterval and add up will be our composite rule. Right. Now let us look at the composite trapezoidal rule. This trapezoidal rule we saw that was not efficient. Now what if we perform a composite, if we perform the composite rule to the trapezoidal rule, it will become composite trapezoidal rule. So let's look at it, and we will reproduce this same result using the composite trapezoidal rule and see the improvement that we will obtain from 4. Okay, so let's look at the composite trapezoidal rule. So the composite trapezoidal rule goes as follows. We take our interval AB, we partition it into subinterval xk, x plus 1 of length h, which is b minus a by n. So you can see that if n becomes very large, we can reduce our h. Right? So we assume that the point of the partition are equally spaced. So xk will be written as 1 plus kh. Okay, so this is what our Simpson composite trapezoidal rule will give us. It will be h by 2 summation fxk minus 1 plus f sub xk. F of x sub k. So this is the rule here. So how do we get this one? We just apply Simpson rule to this one. I mean trapezoidal, not Simpson. To this interval. So let me quickly write it down. So if I apply Simpson to this interval, I say Simpson trapezoidal. If I apply the trapezoidal to this one, so the integral from you agree with me that if you take a trapezoidal, it will give us h, and what is h here will be this difference h. That is that is a h. Yeah? Let us just write h. H by 2 f of this plus f sub k. So that this is Simpson. Sorry, trapezoidal rule. This is the trapezoidal. That's our trapezoidal rule over this subinterval. And this h, we know that h will be, that's h. Now, if you apply now to this integral, which we call composite trapezoidal. So the composite trapezoidal for this, we are just going to sum right? As here we say add them up, right? We add up the result. That's what we are doing from this last bullet. So this is the result, we add them up. So we are going to add up what? This integral, which is given by h by 2 f sub k minus 1 plus f sub k. So that's the room, right? Okay, but now what is that else equal to? Because remember, if I take a partition like this is A, this is B, let me take this inner point okay. You see that if I integrate from this to that point, from this, okay, let's call this xk minus 1, and then this one xk. Now, you can see that if I integrate over this first subinterval, this is xk minus 2. If I apply this, you see that over this xk plus 1, I will do this. I will integrate from xk minus 2, xk minus 1. That will be for this first one. Now, if I integrate for the next, that will be from xk minus 1 to xk. So you can see that these two integrals these two have the same point, xk minus 1, xk minus 1 here. You see? So when I will be summing, xk minus 1 will be repeated twice. So that is true for any interior point. I just took this one. You see that these two subintervals share xk minus 1 as an interior point. So even if I take this first and the second, they will all share. So all the interior points except A and B will be summed twice, right? Because if I take this entire summation, all the inner points will appear twice in the summation. right? So that is why when we perform the summation here, because you can see that in this formula we have this. You see, we have this one. I can take h by 2 out of the integral. That's what we have here. And now this summation, all the interior points except a and b. So for a and b, you can take a and b out. The remaining one will be summed twice, and that's exactly what we have here. You see, for k equal to 1 to n minus 1, h by 2 will be multiplied by 2 because it will be twice f of that. So we have h by 2, this common h by 2, times twice the f of xk inside. But those ones will appear twice. So that's why these 2 and this other 2 cancel out, and you only have h here. Right. I hope you understand the formula. You understand why we can represent it in two forms. You have the first one where you have this summation, but we can group, we can extract f of a and x of b, and whose factor will be h by 2, and the remaining whose factor will be h. So it comes from this summation. Okay, so that's for the composite Simpson's rule. Now, let us go back to our comparison. Not the comparison per se, but let us go back to the improvement of this first example. You recall this example where we blindly apply the trapezoidal rule with a single subinterval, and we found that the result was not good. It was 4. Now, what now if we apply, if we apply a partition of the interval, that is, we take many subintervals and we apply the composite Simpson rule. What improvement will be observed? So that's what we are looking at now. So we take h to be 2 by n, right? Because we saw that h is b minus a. So this is our interval. B is 0 and a is, sorry, a is 0, b is 2. So h will be 2, that is b minus a, 2 divided by n. So that's exactly what we have here. This is your h. And these are the points. See, x0 is 0, so x of I will be 2i by n. Now, because h is 2 by n, so we can replace by this. Now, we substitute this expression in our Simpson rule. Right? We know already the expression of our Simpson rule, so we just substitute there. H by 2 is 2 by n by 2, so it will be 1 by n, because the 2 cancel out, will be 1 by n, which we have here. And then we have f of 0 here and f of b there, f of a, f of b. And then the remaining term there, which is twice the sum of the interior point. So this, we rearrange, we get this expression, right? And we know that the sum of I squared will be equal to this expression by 6. And we add the 1, this 1, and we have this factor 2 by n squared. So if we cancel out the sum of the terms, like here you have 2 and 6. So 6 is 3 by 2, so if we cancel 2 and 2, it will be this numerator by 3n. And n squared, we cancel out with the n in the middle here. So we can expand that, we get this expression. So you can see that our trapezoidal rule is now written in terms of n. We can now vary the number of subdivisions, because n here represents the number of subintervals, right? We're using n subintervals. If we take n equal to 1, obviously the result should be 4, because remember that in the previous example here, we used n equal to 1. There was only one subinterval here. So that's why we got 4. So let's check if we take n equal to 1. If n is equal to 1 here, so TF 2, right? That is h. H is 2. Will be equal to what? N is 1. So this will be 3, right? This will be 2 plus 1, 3. And that 3 will cancel out with this 3, it will be 4. So you see, it's an agreement with what we did previously. Now, if we increment the number of subintervals, we take n equal to 5, we can see that it's getting closer to the exact number, because remember that the exact value is 2.66667 here. Now you can see that if we take 5 subintervals, we are getting closer. If we take 10, it start converging. If we take 15, 20, you see, so there's convergence. It's converging already. So with this one, you can see the power of the Simpson the composite trapezoidal rule, or any composite formula can play with the number of subintervals, and then you improve the convergence. Simpson rule, trapezoidal rule, which does not converge, can be converging if we use the composite version of that rule. Now, if n goes to infinity, you can see, this is a sequence. You know that if you take n to infinity, it will just be the ratio of the leading term over the leading term in the denominator. The leading term here is 2n squared, sorry. So the leading term will be, so we already have 4 here as a factor. The leading term here will be 2n squared, and in the denominator you have 3n squared. You can see that the n squared will cancel out, right? And it will give you 8 by 3, which is the exact value. So you can see that when n goes to infinity, this composite trapezoidal rule will converge to the exact limit, which is the exact value of the integral. Is it clear? Is there any question? I think let me stop here for now and make sure that you understand. Is there any question? Is there anything that I explained you don't understand? Yes, I'm listening. Is there anything that I explained that you don't understand? Yes, I'm listening. Can you ask questions? Johannes, is everything clear?
So I can only ask a question probably tomorrow when I go through to see exactly what it is that I don't understand. After I go through everything, the notes, today's class work.
Okay, no problem, no problem. Kashupi?
Sir, I don't have any question.
Okay,
Let's
good.
in a comment.
Ngishe yelike. Yeleke.
No question.
No question. Great. I think we can stop here for today. Tomorrow we will continue with the Simpson trapezoidal rule. I want to stop here so that you go and read and try to do the problem. We redo what we did today. Go through those examples. Make sure that you can do that on your own, right? And then tomorrow we'll add more. Okay, thank you so much for your kind attention. God bless you and see you tomorrow afternoon. Bye bye.